If you have ever looked at the guts of a computer, even, conceptually, the basic ingredients,
Yeah.
the AND gate, the OR gate, and the not T gate.
The classic trinity.
Exactly. This logic system, it's the foundation of every single digital device you touch. Your phone, your bank server, a supercomputer. It just feels eternal.
It feels eternal, but it was actually a choice. The structure of all modern digital architecture was largely defined by a decision made by George Boole way back in the mid-19th century.
A single decision.
A single decision. And for 150 years, we've been building on that exact patch of intellectual ground.
Okay, let's unpack this. Because the sources we've gathered show that in the world of specialized high-performance computing, specifically advanced cryptography and the rapidly emerging field of quantum computing,
Right.
that 150-year-old foundation is starting to crack under the pressure. The AND-OR system is just proving inefficient, and it's forcing the emergence of a new, mathematically superior star, the exclusive OR, or XOR gate.
And this deep dive is all about that historical road not taken in digital logic. We're going to explore the incredible mathematical framework that underpins this XOR revolution, specifically the power of Zagalkin polynomials.
And also why the massive inertia of our established systems is making this necessary paradigm shift so incredibly difficult.
Our mission here is to show you why XOR must now be treated as a fundamental pillar, not just a derived function for the next generation of silicon.
So to really understand this shift, we have to go back. We have to revisit the historical origin story.
We do.
When George Boole first set out to create an algebra for reasoning, he didn't immediately land on the AND-OR standard we all use today.
No, not at all. His original system was actually built around AND and XOR logic, which mirrors standard arithmetic algebra much more closely.
And this is the critical historical fork in the road, isn't it?
It really is. Boole abandoned his original, you could argue more mathematically elegant AND XOR system for the AND-OR system that became the standard.
Why? What was the reasoning?
Well, his core reasoning was that AND-OR logic just felt more intuitive. It seemed to align better with the patterns of everyday human language and, natural thought processes.
So the foundation of our entire digital world was chosen based on readability and intuition, not necessarily ultimate computational efficiency.
Exactly. And that choice became an unmovable fixture. It defined how we teach logic in every engineering curriculum globally, and it dictated the entire development path for the electronic design automation, or EDA, industry.
And this leads directly to what we're seeing as the central failure of the standard logic today, especially for certain types of functions.
Right. Standard circuit synthesis, it relies on the sum of products form, the SOP form. That's where a function is written as an OR of a bunch of AND terms.
An SOP is fine for base control units, for what we call random logic.
It's fine for that. But for arithmetic and for parity functions, it is disastrously inefficient.
This is what the sources call the parity paradox. And it just perfectly illustrates the exponential complexity trap that we fell into.
It's a fantastic example. Imagine you need a simple n-bit parity function. So the output is 1 only if an odd number of the inputs are also 1.
It's okay.
If you try to build this using the standard SOP, the AND-OR method, the complexity just grows exponentially. A 10-input parity function would require 2 to the power of 9.
So 512.
512 separate product terms. It's a massive circuit blowup.
But if you use the XOR form,
the complexity drops straight to linear. For that same 10-input function, you only need 9 XOR gates.
9 versus 512.
It's an astronomical difference, especially as the number of variables increases.
So why didn't this matter earlier?
Well, early on, it wasn't a huge issue because the physical CMOS implementation of a single XOR gate was historically a bit more complex than, say, a simple NAND gate.
Right, it took more transistors.
It did. But that marginal difference in physical complexity has been absolutely dwarfed by the massive logic gap that arises when you are forced to build functions like cryptographic components using the old, inefficient SOP method.
So the math penalty just started to far exceed the silicon penalty.
By orders of magnitude, yes.
That makes perfect sense.
Yeah.
I mean, if the problem is fundamentally rooted in the gates themselves and how they represent addition, it sounds like we just hit a wall with the standard physical gates.
We did.
So if the gates are the problem, where do we go next? Is the solution purely mathematical?
It is. We have to leave the logic gate diagram behind for a moment and move into a cleaner mathematical space. And what's fascinating here is that the mathematical engine driving this revolution is the algebraic normal form, or ANF.
Also known as Zagalkin polynomials.
Exactly. This framework treats Boolean logic entirely algebraically within something called a Boolean ring over the Galois field GF2.
Okay, hold on. Galois field GF2 sounds incredibly dense. How do we, as listeners, ground that? What's the practical, everyday way to think about that remapping of operations?
Think of it simply as algebra without carry. We are remapping our three core logical JITs to algebraic operations that just behave better for specialized computing.
You take XOR.
Logical XOR, the circle plus symbol, becomes regular algebraic addition, the plus sign.
Right.
Logical A and D becomes algebraic multiplication, a dot. And logical not T, so not X, is simply represented as 1 plus X.
And because it's GF2, which means all results are basically reduced modulo 2, the algebra gets those strange but crucial rules.
Exactly. The first key rule is X plus X equals 0.
Right. 1 plus 1 is 0.
Just think of that as modeling the XOR gate perfectly. If you add 1 plus 1, the result is 0 because there's no carry. And this self-inverse property is key in logic synthesis because it means we can remove redundant terms from an expression just by canceling them out. It dramatically simplifies the circuit.
And the second rule is X times X equals X.
Right.
Idempotency.
Right, and these two rules, together, they ensure that any Boolean function, no matter how complex, can be uniquely represented as a polynomial. It's like turning a messy circuit diagram into a guaranteed simplest possible equation.
And that uniqueness is profound.
It is. And what the sources show is that the practical application is surprisingly elegant. You don't have to derive this polynomial by hand.
So how do you do it?
You can use a direct computational method. It's often related to the Reed-Muller transform that uses a matrix, the Zagalkin matrix, to convert a function's truth table output vector directly into its unique polynomial coefficients.
So that's the mathematical fingerprint you mentioned. Let's look at a concrete example from the source. You can take the 8-bit output vector from a 3-variable function, say y equals 1, 1, 0, 1, 0, 0, 0.
Yep.
You run it through this transform, and out comes a set of coefficients.
And that result defines the function uniquely. In this source example, the resulting unique algebraic normal form is f of by 2 by 1 by 0 equals by 1 plus by 2 plus by 0 times by 2.
And that equation is the canonical form of the function.
It is the function.
Which brings us directly to optimization. Because once we have the polynomial, we don't just translate it into gates. We manipulate it algebraically to minimize hardware use. And here's where it gets really interesting, because the goal of minimization completely changes depending on the application.
Yes, look at advanced cryptography, particularly protocols like fully homomorphic encryption, or FHE.
FHE. For listeners who haven't encountered it, FHE is kind of the holy grail, right? Performing computations directly on encrypted data without ever decrypting it.
It is the holy grail. And the reason the XOR ratio is so important in FHE is that for protocols like this, the AND gate is vastly more expensive than the XOR gate.
More expensive how?
The AND operation intrinsically creates a significant amount of noise or error in the underlying cryptographic scheme. And that noise is really expensive to manage. It requires complex, resource-intensive cleanup operations.
So the entire optimization goal just completely shifts. Instead of minimizing total gates, which is the traditional goal, the focus is reducing what's called multiplicative complexity, or MC.
Which is just a fancy way of saying the total number of A and D gates, or the degree of the polynomial.
Right.
Precisely. I mean, the sources document cases where engineers will intentionally add hundreds of cheap XOR gates just to save a single A and D gate. The cost asymmetry is that severe.
And how do they do that?
They use algebraic factoring techniques like trading one larger A and D term for smaller terms that combine XORs and smaller A and Ds. For example, changing AB plus AC to a times the quantity B plus C.
This mathematical form isn't just about efficiency in crypto. It's also the gold standard in formal verification.
Absolutely.
Because the Zagalkin polynomial is a canonical form, that unique, unambiguous mathematical fingerprint you mentioned, it offers guaranteed equivalence checking.
That's right. If you have an original circuit design and then you optimize it using some complex new process, how do you prove they still do the exact same thing?
Right. Simulation can miss corner cases.
It can.
Yeah.
But if you convert both the original and the optimized version into their algebraic normal forms, and the resulting polynomials match, with 100% certainty that they are functionally equivalent. This level of rigor is absolutely crucial for hardware security and IP protection.
And if we connect this to the bigger picture, the shift to XOR logic isn't just optimization, it's preparation for the future. The next generation of high-performance computing, particularly quantum, is fundamentally built on this idea.
It is. The primary quantum gate, the CNOT, or controlled NOT gate, is functionally equivalent to a controlled XOR gate. For quantum computing, thinking in terms of XOR is not an optional optimization. It's the native mathematical language of the machine itself.
So you can't build scalable quantum circuits without embracing this algebra.
You really can't.
Okay, now here's the big friction point. If the math is so superior for arithmetic security in quantum systems, why haven't we switched entirely? Why is the ANDR standard still dominating, 95% of logic design?
Because the existing system has massive inertial resistance. You can think of it like an entire nation having its infrastructure built on a standard railway gauge. Even if a new gauge is mathematically superior, the cost of replacing every single train, every track, and every station instantly is prohibitive.
Right, and the technical challenges of switching are immense. Let's start with what the sources call the OR gate explosion.
The explosion is a real problem. The Zell-Galkin domain, this A and F world, has no native logical OR gate.
Not at all.
No native OR. To represent a simple logical OR, A or B, in A and F, you have to express it algebraically as A plus B plus A times B.
So you get an A and D term in that.
You get an A-D term. So for standard control logic, which relies heavily on OR gates, translating it into A and F can cause an exponential blow-up in size. You might make the arithmetic section beautiful, but the control section becomes impossibly huge.
And the XOR function itself is fundamentally different from AND and OR,
Yeah.
which complicates optimization, right?
Absolutely. XOR is non-monotonic. In standard logic, if you have a massive A and D gate and one input is 0, the output is instantly 0, it masks everything else.
And designers rely on that for optimization using don't care conditions to simplify things.
They do. But in XOR, every input toggle always propagates to the output. There's no masking. This non-monotonicity makes traditional logic pruning and don't care optimization far, far more computationally complex in the XOR domain.
Plus, finding the absolutely minimal circuit representation called the exclusive sum of products, or ESOP, is an NP-hard problem.
A very hard problem. The established algorithms for minimizing SOP are incredibly fast and mature. In contrast, the sources note that exact ESOP minimization is currently only feasible for very small functions, sometimes 7 variables or fewer.
So we simply don't have the tools to guarantee the best possible circuit for large XOR-heavy designs yet.
Not yet. And beyond the technical hurdles, we face these cultural and economic resistances, which the sources break down into 5 main categories. This is the human element of inertia.
The first is education. The AND/OR curriculum isn't just a textbook. It forms a deep-seated cognitive barrier. It's the only way an entire profession has been trained to think about circuits.
Second is the entrenched tool chains. We're talking about decades of proprietary EDA software, millions of lines of code optimized specifically for minimization algorithms that prioritize the old standard, like Quine-McCluskey. Overhauling that is a massive, multi-billion-dollar sunk cost that few companies want to tackle.
Then there's the persistent cost bias. This decades old, but you're saying increasingly obsolete belief that OR gates are always cheaper in silicon than XOR gates.
Yeah, that bias is being eroded by modern fabrication. New techniques, particularly using structures like pass transistor logic or PTL, have dramatically reduced the transistor count difference between an OR and an XOR.
So the gap is small enough now that the algebraic efficiency should dominate the design choice.
It should, but the old bias remains in many legacy design teams.
Okay, the fourth point is just human habit. Boole's original reasoning still holds water. AND/OR aligns better with human intuition. If you try to write control logic using only XOR, it becomes really difficult to read and verify quickly.
Designers prefer tools and logic systems that match how they intuitively approach a problem. It makes sense.
And finally, the fifth and perhaps most powerful resistance, the psychological barrier.
Just plain old, why bother? When faced with this gargantuan task of restructuring an entire global digital industry, the attitude often defaults to, the existing system is good enough for 90% of what we do.
So what does this all mean for the person listening to this deep dive? It sounds like the future is not a painful universal replacement of AND/OR with AND XOR,
No, not at all.
but rather an intelligent synthesis of the two.
Absolutely. The leading edge of the industry is already bridging this gap. Modern logic synthesis tools like the Berkeley ABC system are now integrating these paradigms seamlessly.
So how does that work in practice?
They have specific commands. For example, a command like rewrite Z that invoke these XOR-centric algebraic methods, but only when the tool recognizes functions like parity generators or specific cryptographic components, where A&F optimization is mathematically essential.
So we are essentially revisiting a fundamental choice made 150 years ago. Not because the choice was wrong then, but because the scale, the complexity, and the specialized nature of the problems we're solving now, from hardware security to quantum entanglement, they demand the mathematical efficiency that Boole set aside for the sake of human intuition.
Right. The road not taken wasn't a mistake. It was simply a path whose time has finally come.
And here's a thought for you to chew on. If we know that the initial choice of fundamental logic determines what optimization goals are prioritized and what kind of solutions are easy or hard,
Hmm.
and we see how critical anti-XOR minimization is for security and arithmetic, then consider the broader impact on general computing.
Yeah, what's the fallout?
How much unnecessary complexity or wasted energy or sheer number of transistors might still exist in non-arithmetic chips today, simply because our entire digital world was built to optimize for a logic system that was selected based on human language habits rather than ultimate mathematical efficiency. What other digital inefficiencies are hiding in plain sight?